So it turns out that push and pop also need to use the ALU because they need to increment or decrement the stack by 8. In fact, not only do push and pop need to use the ALU, but call and return also need to increment or decrement the stack by 8. And here's the bigger surprise. We're going to use the ALU to add 0 for a couple of other instructions, in particular, the register-to-register move and the IR move queue. Now, you might think that it's kind of dumb to use the ALU to add 0, but what we're going to find is that by being consistent and having a lot of our instructions feed values through the ALU, we can actually reduce the wiring and allow val-e to get written directly to the register file for a larger class of instructions. So the way we're going to implement this is we're going to have to think, when we increment or decrement the stack, where is the value of the stack pointer, and therefore, where do we have to feed the plus or minus 8? So the stack pointer is going to come out of val-b and get fed into ALU-b, which means we want the plus or minus 8 to go into ALU-a. On the other hand, for the immediate or register-to-register moves, the register that we're reading is in val-a and is going to go into ALU-a. So ALU-b is going to have the 0. And so we normally get val-b into the ALU, we get the 0, and now we need the input to make a decision about which one to pick. We're going to have to extend our I-code circuit, or our I-code signal, to also go into the ALU. So now we can implement push and pop, call and return, and also the register-to-register move and the immediate-to-register move, all sort of using the same circuit. What have we forgotten? The condition codes. Now, I just got through telling you that we're going to use the ALU for all these different instructions, but in fact, we only want to update the condition codes if we did an ALU operation. So if we use the ALU for address calculation, we don't want to update the condition codes. Therefore, we need this logic block, which is going to say, do we set the condition codes or not? And it will be driven by our same friend, the I-code signal, which contains the opcode. Are we done? Very close. What do we do with those condition codes? Well, the condition codes are going to be used to help us decide whether we take conditional jumps or whether we do conditional moves. So we actually need to take the output of the condition codes and feed that into a piece of logic, which we're going to call con for conditional, that takes the function, and then given the function and the particular state of the flags in the condition codes, particularly the Z flag and the S flag, and then computes whether, given the state of the flags and the function that we want to do we want to do the operation or not? In other words, do we want to take the jump or not? Do we want to do the conditional move or not? And so that's the last piece of logic that we're going to need to implement in this execute phase.